So the very first slide that you see here shows the devastation of coral reef on a very large scale by man-made events, for example, using blast fishing or mining for coral. Now, I will show you later the role of steel in solving this problem, but I'll begin with something that is a bit more topical. You will have all heard of the collision that happened in the English Channel, quite close to Britain, where there was a tanker which was stationary, carrying jet fuel for the American military, but it was anchored. And along came a container ship known as the Solong, and it hit the tanker at approximately 90 degrees. So why did this happen, given all the modern technology that we have for navigation and so forth? That I don't know. But what I'm going to show you is how brilliantly the steel out of which the ships are made of managed to contain the disaster. And this was very recently, 10th of March, 2025. This is the damage that was caused to the tanker, massive damage. And what I want you to note carefully is how the steel has actually deformed. It's really got into a convoluted shape, fractured into a large gash, and so forth. And that is really quite important because the deformation of the steel absorbs energy. And notice that this ship is still afloat. And indeed, both ships remained afloat and were towed into harbor somewhere in Britain. Now, this level of damage can only be sustained by something like steel. There's no other material which can take this level of damage and yet keep the ship intact. So I'm going to demonstrate this with a short calculation. So this is undergraduate stuff where we know the speed at which the Solong was proceeding. It was 16.6 knots according to the interim report of the National Maritime Agency, and I've converted that into meters per second. And it weighed approximately 8.5 million kilograms. So you can work out the kinetic energy of the Solong, which comes to about 300 million joules. And that kinetic energy must be absorbed by the Stena Immaculate tanker. So the ship steel absorbs stress times the plastic strain joules per meter cubed. So if I take the typical strength of a ship steel, around 300 megapascals, and its fracture strain, then the steel here is able to absorb 90 million joules per cubic meter of steel. Now, of course, we are not dealing with a cubic meter of steel, so I have to convert it into an area corresponding to the plates used for making this ship. So we need 3.3 cubic meters of steel to absorb the energy of the impact. And the thickness of the hull steel is 12 times 2, I'll explain the 2 later on, millimeters. And therefore, a very easy calculation tells you that about 9 meters of steel must suffer, and that's approximately the scale of this gash in the side of the ship. So steel is incredibly important in its ability to absorb energy during deformation. That simply isn't true, for example, for graphene. When you break it, you recover all the energy elastically, and in any case, graphene loses its strength as soon as you scale it up. So the ability to absorb energy is really to do with the metallic bond of steel, because you can have layers of atoms sliding over each other without actually disrupting the bond at all. And this principle comes into your everyday lives. So for example, when you have a head-on crash, there is a system within the car that would enable the steel to crumple and absorb energy. That's if you have a head-on crash. So, if you look at this image over here, the actual compartments, passenger compartments, are hardly damaged, and people can walk out of a crash like this. It depends, of course, on the speed, etc. And even from side impact like this, there is reinforcement inside the steel door, so that the penetration of the car which impacts the other car is not very large into the passenger compartment. And you may not know this, but the amount of steel in cars has actually increased because of these safety requirements. It hasn't decreased. So if you follow the weight of cars going back to the oil crisis, this actually has increased with time because of the safety measures. Now, in the case of trains, and I don't have time to show you a movie, but you need to absorb a lot more energy. And there is a special steel known as a trip steel, which becomes extruded during a collision, and that absorbs the energy of impact of a train. Now, going back to the ship, the Stena Immaculate, this is a picture of that ship before the collision. And it was made in China, owned by Stena, and operated by the US. And the collision, even though it was carrying jet fuel, caused very little pollution. And the reason is the design of the ship. So the fuel is actually in 18 tanks. And it isn't clear, but maybe one and at most two of these tanks were ruptured during the collision. And the ship also has another safety measure, which is that it has a double hull. In other words, if you penetrate one hull, you might still have the second hull intact. Of course, this means you're using double the amount of steel, but that's another story. Now, the collision itself produced very little pollution, and there was a fire as well. And I wanted to do a brief calculation of the temperature reached at certain locations when you have that collision. So I looked up some literature, and there was some nice work done at Surrey University on two spherical balls rubbing together and the temperature at the contact area. Now, of course, that isn't the same as a ship, but as you'll see later, these approximations don't matter, and I've discussed them with the people at Surrey University. So they calculated that the temperature rise due to a collision, due to two spherical balls rubbing against each other, will be given by this equation. And we have all the data for ship steel. It's a friction coefficient of about 0.4. This is actually a dimensionless velocity. This is a thermal diffusivity, and we know the velocity of the so long ship, and we know the thickness of the steel. So I've assumed that the rubbing surfaces would correspond to the thickness of the steel, and that comes to a very impressive 1200 Kelvin momentary temperature rise, which is far greater than the spontaneous ignition temperature of jet fuel. So even if my calculation is wrong by 500 degrees centigrade, the jet fuel will definitely ignite, and that is the reason why we had the fires. And because the fuel spilled onto both ships as a consequence of the impact, both ships were on fire and were abandoned quickly, although there was one tragic loss of life. Now, I mentioned that the tanker was double-hulled, and that is a safety requirement for fuel tankers which operate in anywhere near territorial waters. But it is wasteful on the use of steel. If we could have steel which is capable of absorbing all that energy, but single-hulled, that would be so nice. But to design a ship steel is not easy, okay? Of course, you need strength, all right? So ship steel typically is 300 megapascals in strength, and that means that it can support the weight of 300 million apples on 1 square meter. We can, of course, make steels much stronger than this, but you also need to be able to weld to join the steel. And that means that you mustn't have too strong a steel, because it would crack in certain areas due to the heat input during welding. It must be tough, of course, that goes without saying. That means it must be able to deform and absorb energy, and you must be able to make it in large quantities. So people have worked hard on designing a ship steel for which you could use just a single hull ship. And that has happened. So we can now greatly increase the ductility of ship steel. You can see the strength is about 400 megapascals. And the reason is that, the conventional ship steel has a structure like this, which is ferrite and pearlite. Pearlite is simply a mixture of hard cementite and ferrite. And because there is a big difference in strength between the ferrite and these hard regions, they don't deform homogeneously, and therefore you have limited ductility in a tensile test. But if you make these hard regions more homogeneous by introducing new structures as well, then you can get much greater ductility. And this is Kazutoshi Ichikawa, who was my PhD student, and Kazu Hase, who was a visiting scientist in Cambridge. And they have designed a new ship steel, which has much greater ductility than conventional ship steel. Now, the test that I've illustrated here is very simple to do, but we really need to do much better than just a tensile test, because all these authorities which govern the construction of ships and the safety of ships and the regulations of how you construct them, etc., they must be satisfied, which means that you must be able to do tests on a large scale. So what is the scale of testing that we need to do? Well, first I need to introduce you to some hydrodynamics as a ship goes through water. So this is an old warship, and this is a wave which we call a bow wave. Now, this isn't a real bow wave. They painted it onto the ship to give the appearance that the ship is going fast, okay? But what happens is that as the ship displaces water, a ship which is shaped like this displaces water, the wave is created here, which exerts a drag on the ship. Now, this may not be too important in the case of warships, but in the case of cargo ships, this is significant, and you will use up a lot more fuel than you would do if you corrected somehow for the creation of this bow wave. So you have this strange object at the bottom of civilian ships, cargo ships. This is a bulbous object, and the reason for putting that under the ship is that it creates, it displaces water so that it creates a wave like this, which compensates for the bow wave, which is created when the profile of the ship is like this. Here, exactly compensates for that. So you no longer have a bow wave, and therefore you can traverse the water without much drag. But this is poking out at the front of the ship, and that is the bit that would hit another ship first. Okay, so in a sideways collision like that, this actually would penetrate the other ship first rather than the infrastructure above. So we are looking to simulate a blunt impact. Okay, and at Nippon Steel, they did this. So this is a conventional steel, and this object will push against this plate, and you will see that the conventional steel, after a certain amount of penetration, oops, sorry, I'll do that again. Yeah, after a certain amount of penetration, you will see fracture at the top, where water can come in or oil can spill out. And that is the reason why we have double-hulled ships. But with the new steel, with much greater ductility, if you look at the same test, then there will be no fracture for the same amount of penetration. Okay, wonderful. So this steel is capable of absorbing much more energy during plastic deformation before fracture than conventional ship steel. And back in 2014, the first of these ships was built and successful, and something like 30 or 40 more ships have been built using the new steel, and you get concessions from insurance authorities, etc., if you use this new steel. Now, to change the topic, not so long ago, we had the Twin Tower disaster, where very tall buildings were hit by an aircraft and a fire happened. Okay, now buildings have to comply with a requirement that the steel must continue to support the structure for 1 hour in the event of a fire. And that's exactly what happened with the Twin Tower, that almost, remarkably close to 1 hour with the fires raging on this floor, basically this steel completely lost its strength and the top half collapsed onto the bottom half, leading to a huge shock, which was recorded on seismic devices all over the world. And that is what caused the whole building to collapse. Now, the steel is not on its own in buildings. It is actually covered with fire protection as well on all its important surfaces. And that fire protection is a requirement for any building using steels. Now, this is another design of the sort of beams that we use in buildings. So you can see that the top and the bottom are not of the same length, whereas a normal I-beam has these flanges of the same length, and you put the floor on top of the beam. In this case, we can actually slot the floor into this gap here and put all the surfaces through there. So you don't need fire protection on these surfaces, only on the other surfaces here. Furthermore, you save height. So for the same height, you can have more floors of equal height to any other building if you use a beam like this. And we developed this with British Steel several decades ago. And we had to put up a building. British Steel had to put up a building and set it on fire to prove that it would survive for 1 hour in the event of a fire. Now, of course, it doesn't necessarily mean that everybody will be able to escape from the building, because you have other consequences of fire like smoke and so forth. And sticking with the story of steel buildings, of tall buildings, this is a movie that I took by putting my telephone flat on the dining table in a 60-story high building where I was on the top floor. And I noticed that the candelabra, this was in Moscow, the candelabra started to shake because the weather outside was really rough, heavy rain and strong winds. Now, why is this happening? Well, when you have a tall building, just the elastic deflection of the beams, not plastic, but elastic deformation accumulates, almost like when you take a plastic ruler and you bend it, the displacement is much bigger at one end than at the end that you're holding it. So this vibration under the influence of winds or earthquakes can become very large as the height of a building becomes bigger and bigger. So this is, for example, the Taipei 101 building, which has 101 stories. It is the tallest building in Taiwan, and at the time it was built, it was the tallest building anywhere in the world. So how do you cope with stopping it from shaking at the top? And also, this is an earthquake zone. Now, I was very lucky to be able to go into this building while it was being constructed, because my former students were involved in the project. And this is a very interesting structure that was placed into the building. It is a steel ball weighing something like 650 tons. And it's suspended from the top, from the 92nd floor to the 87th floor, to act like a tuned damper. So it effectively dampens any tendency for the building to shake at the top. And notice that this is during the construction stage. And later on, they realized that this is actually really quite a good story. The Taiwanese realized this is a nice story. Let's paint the ball gold. And here you are. The ball is painted golden, and it's a tourist attraction. So you can see that the 600-ton steel ball is suspended from these incredibly strong steel ropes, and it's connected to silicon oil dampers here. So it compensates for the vibration of the building. And what I'm going to show you next is a movie of how this performed during a large earthquake. So you know that the magnitude of an earthquake is defined in terms of a Richter scale, and that was in 1935. Richter 6.8 means you get a displacement of tens of centimeters to a meter at the epicenter. Okay, tens of centimeters to a meter. Taiwan had an earthquake with Richter scale 6.8, and this is how the ball performed. So nothing at all was damaged. Nothing at all was damaged in this process. The ball took the vibration caused by the earthquake. Now, switching to nuclear accidents. You know, the first two major nuclear accidents happened in British domains. Okay, the first one was in Canada at the Chalk River Laboratories, or research facilities. And this is one of my students. This facility is still open. And this is one of my students who went there to do neutron experiments. And basically, in the early days, the steel control rod system failed, and there was a partial core meltdown. But it was managed, and recovery took place, and the laboratory functions perfectly well right now, and everybody can go there if they have a good scientific case to do important experiments using neutrons. The second disaster was in Britain, in the Windscale, and this was much more serious. It was in 1957, where the steel containment of the reactor remained integral. But the reason for this disaster was interesting, that irradiation causes damage in the metal surrounding the nuclear fuel. Fast neutrons will displace atoms out of their normal equilibrium positions and so forth. So periodically, you actually anneal the reactor by allowing its temperature to rise so that the defects are removed effectively. And that's called annealing, and it releases an energy known as a Wagner energy. So at Windscale, they were trying to do this annealing, and the temperature went out of control, and you had a partial core meltdown with 10 tons of radioactive fuel melted, 10 tons of it, and lots of radioactive stuff released into the environment, detected in many European countries and so forth. And that is the reason why we no longer call it Windscale. It's called Sellafield now. They changed the name because this was an epic disaster. But the steel containment of the reactor remained intact, okay, completely intact, not damaged by the meltdown. Now, of course, Chernobyl was another very serious accident, a reactor accident, again during a stress test of the reactor. And there was a power surge, explosions, and massive release of radioactivity. So the first procedure was to cover the affected area by a concrete sarcophagus. Sarcophagus comes from ancient times, where it's a stone container for a dead body. So it was encased in concrete, constructed in just 6 months back in 1986, and enclosed 216 tons of radioactive materials, but the concrete deteriorated progressively. So a new sarcophagus was erected, made out of steel, with a predicted 100-year lifetime. And I emphasize predicted, and I'll show you why I emphasize that later. But the engineering involved was amazing, because obviously you can't be at the reactor to construct this huge, massive steel building. So what they did was they constructed it away from the reactor and then took it on rails, a very slow journey, so that it went on top of the reactor. And this is the actual construction of the sarcophagus: 25,000 tons of steel, 500,000 steel screws, and designed to operate perfectly okay, plus or minus 45 degrees, force 3 tornado, which has 165 miles per hour wind, and 3 outer layers of stainless steel there. And it was rolled into position. And this is actually now in position of the reactor. And it's not empty, you know, there is structure inside, like cranes and so forth, because what they're trying to do is to dismantle the concrete and make it safe. And the construction began in 2010 and was completed in 2017. Now, unfortunately, you know, people, mostly in Europe, but in many places in the world, have not learned to live in peace with each other. So in February 2025, there was a drone attack on this structure, which caused a 15-meter diameter hole, but only in the outer roof cladding, and another 300 holes, which were 30 to 50 centimeters. The internal cladding in the roof ignited, and it took 2 weeks to extinguish the fire, but no radioactivity escaped, or there was no harm to the environment. But imagine that if there was sustained attack on this, then we would have huge problems once again. The crane system inside was damaged. You know, they do remote work inside this building to make things safe. But hopefully there will be no further attacks on this, because there's no steel that can survive modern weapons. You know, tanks are basically useless as weapons. You can knock them out easily unless you are fighting against civilians. And of course, very recently, we had these bombs dropped onto the Iranian nuclear facilities, and we don't know what will happen to the radioactive materials inside, which obviously will have a pathway to the outside. I don't know. So steel is very good at helping us in disasters, but it cannot cope with you know, the fact that we cannot live in peace. The Fukushima earthquake was another nuclear disaster, but it was not at all due to steel. You know, basically the massive steel reactor pressure remained intact, the containment vessels remained intact, the steel liners of the spent fuel remained intact. The problem was, you know, we use zirconium to contain fuel, nuclear fuel sometimes, and that reacted with the water which came over the flood defenses into the reactor and created hydrogen, which led to an explosion. But the explosion did not destroy the steel pressure vessel. Okay, so you know, war and massive natural disasters, it's very difficult for anything to cope, any material to cope with events like that. Okay, going back to this damaged coral reef, you know, and I got this story directly from the BBC, and then I contacted the people working in this area. So Indonesia has a very large a large coral reef area, and a substantial amount of it was destroyed, you know, in the past when regulations weren't tight, by dynamite fishing or by mining for the coral for buildings. So what do? So some very clever people took some steel, you know, dirt cheap steel, right, and made it into objects shaped like this. And the reason for making it like this is that it would stay on the seabed, and steel has a high enough density, it wouldn't be washed away by storms, etc. And all you do is you attach bits of live coral to this and you leave it. There's nothing more you need to do, okay? And the picture that I'm going to show you next is absolutely true at the location where the coral was completely damaged. And this is what happened, okay, after a few years. the coral grew, recovered completely, and you can still see here the remnants of the steel that was holding the seed corals. Now, disasters can be of many kinds, and some of them are personal. And people in Cambridge certainly and elsewhere will know that if your bicycle is stolen, right, then it isn't just the cost of the bicycle, but it causes a trauma because you have to travel, okay? And sometimes it's very inconvenient to go by cars, etc. Bicycles give you complete freedom for travel. Neil Barron created a company which is in Wales, in Swansea in Wales, which I visited. And he has invented an uncuttable lock. So the movie that I'm going to show you is my first attempt to cut the lock, which is an ordinary lock. And then I try to cut the uncuttable lock, and I won't be able to cut it. And then the staff member of the company tries to cut the uncuttable lock, and you'll see what happens. But this is the ordinary. "28 seconds to cut the lock." Now the uncuttable lock. Amazing. The actual angle grinder was destroyed in the blade was destroyed in the process. And this is a company based in Wales which exports these locks all over the world, and it's the only company which makes these locks.
With the final example you showed there with the lock, how heavy is it? Is the lock going to be a transportable type of system, or is it going to be a kind of more, you leave it at your home and it's something that you can use to lock up your bike at night?
That's a very good question. So the diameter is exactly the same. Okay, so they made it as a D-lock because everyone is familiar with a D-lock, but you can find other configurations. I can't tell you the secret because that belongs to the company, but there is a tiny bit more material on the lock. So it's not particularly heavy. Now, the bit that goes onto the end of a D, right? That also has to be good, and the lock within should be a lock which cannot be picked. So all that appears in the so-called light lock.
Brilliant. Thank you very much. And I suppose my other very quick question for the example on the seabed with the recovery of the coral reefs. Is there any kind of long-term effects with the corrosion of the steel and how that might break down? And has that already been designed in so that the system kind of gradually, the requirement for that steel goes away?
So just to tell you how the Earth actually evolved, at first all the iron was dissolved in the oceans, okay? And it's only when little creatures started to produce oxygen, the oxygen couldn't make it to the surface, right? So there was no life on the surface because the iron took it up and became iron oxide, which sinks. Okay, and that's what the Brazilians and Australians mine and sell. Okay, so the iron oxide is not at all harmful and is present there anyway. The corrosion is not an issue because it'll last a lot longer than the time required to recover the reef. So I suppose that if you could make, if you could easily buy these rebars at a much thinner size, which really isn't useful for making buildings, then that would be good.
Brilliant. Thank you very much. We've got a few questions coming in, so I'll start by reading them out. So the first question here, has the weld material or weld process kept up with the advances in steel, or rivets for that matter, asking in the unlikely context of a ship hitting exactly between two adjacent steel plates?
Yeah, so the welding technology is really very sophisticated, and ships are usually welded by arc welding, okay? And that process has been developed to such an extent that the properties that you get not only in the weld metal, but in the heat affected zone are really good. So if you hit it exactly on the weld, there's not an issue. And that's why we need to keep the strength down, because the heat affected zone, otherwise after getting red hot, would transform into a hard material, which would be bad. And in the old days, that's exactly what happened with the Liberty ships. And Mrs. Tippler in the engineering department actually helped solve that problem. You are in the engineering department. Have you heard of Tippler?
I've not come across.
Okay, so you got to, because the Liberty ships, which were coming made in the US, the first welded ships, they would almost break in half. Okay, and the reason is the welding.
Ah, brilliant. Thank
So
you very much.
she actually was key in solving that problem.
Fantastic. I've made a note and I'll go and look it up afterwards. Thank you. So we've got a question here about what is the design concept behind high toughness hull steel? Yeah,
so I showed you the optical structure, which had dark things and light things. Okay, and the dark bits are what's known as pearlite, which is very strong, and the light bits are ferrite, which are much less strong. So when you deform it, the deformation is not homogeneous. Imagine that you've got a hard material and a soft material, and you're pulling, then the soft material will take the strain first, right? And that might create some sort of damage at the interface between the two. So you get ductility diminishing after a certain amount of strain. So by making the harder regions more homogeneous by introducing other phases, you can extend the ductility. And that's exactly what I think happened. Yeah.
Brilliant. Thank you very much. The next question then, steel advances and their applications sound great, but what will the next bottleneck be in the world? Materials, manufacturing, or geopolitical barriers to access?
So steel is abundantly available. In fact, we use indecent amounts of steel. Okay, so there's about 2.5 billion tons produced every year, and a corresponding amount of carbon dioxide. And the reason is that we are using steel badly. We're buying the cheapest material instead of the best material. So I have a plan to increase the cost of steel. I'm working on it, okay? And I've presented it to a small group in the House of Lords as well. If you use more expensive steel, we use less of it, so the total expense goes down, actually, in constructing something. So that is definitely not a bottleneck, but there is no challenger to steel. If you want the quality of life that you have right now, there's absolutely no challenger. Nothing that you do can be done without steel. And, I've been in this business for a long time, and I've heard all material scientists saying, this will change the world. And graphene was the latest, saying we've got something 200 times stronger than steel, which is complete nonsense, So there is no challenger. We've got to use less of this material.
Brilliant. Thank you very much. And I think for anyone that's interested, you mentioned this slightly on the Life Scientific as well with Jim Al-Khalili, and you gave a very interesting talk through your whole life. But also, I remember this point coming up as well, which was it was very interesting to hear about a steel professor that's arguing for less use of their material in a way. I found that quite funny.
But when I was a student and I wrote my first book, we were only using 500 million tons per annum.
Which kind of example are you most excited about, or which example of the ones that you presented do you think that's something that perhaps you wouldn't have foreseen it being used for, or foresee the properties that are now being used in steel being around when you first started your career?
So there are so many examples that I could give you. So for example, in the train collision system, where you actually extrude the steel through a die to absorb energy, so you deform it heavily. It's a very special kind of steel known as a TWIP, TWIP. So it deforms by mechanical twinning, and therefore it can tolerate a huge amount of strain before fracture. You're talking about hundreds of % of elongation before fracturing. And that's why you use it. It is much more expensive, okay, because it has something like 25% of manganese, and that's not the easiest thing to produce. But it can be produced on mass scale, and is being produced on a mass scale for very specific applications.
Does the bulbous nose on a ship contain crushable elements to help absorb energy?
Not that I'm aware of, but bear in mind that I've only done research in a limited way to understand what that bulb is for, not the internal structure of the ship. So there may well be, but I'm not sure. But the idea that, you really don't want collisions of ships, okay? So they are quite rare, in fact. And with modern technology, it really shouldn't happen, but it does. The final report of the National Maritime Agency is not yet published.
In an era of capitalism, how do we communicate to politicians and businesses that we need to use less material?
Trust me, I'm trying very hard, okay? And I've got some help from people to make contacts with the appropriate persons. But it won't be easy because governments have an awful lot on their hands. Many, many other things to do.
What's your favorite material, or your favorite ever application? Sorry, I missed that one.
My favorite material is guess what? Okay, it's definitely steel. There's so much complexity in steels that the head of the Institute of Materials at one point, when we had the 100th anniversary of the in Sheffield of some institute, he said there are 300,000 alloys of iron. Okay, now he was making the case that we need to reduce that. But in fact, the reason why we have 300,000 different alloys is because they all have different applications. Okay, it is so versatile. There is no other material that can match that. Of course, cost is important as well, and it is at the moment it's incredibly cheap. Weight for weight is cheaper than bottled water, and it needs to be more expensive.
And then your favorite application?
It's got to be, the rail in the Channel Tunnel, because I can tell a story to anyone who's about to go to France that, look, you'll be traveling on my rail. Okay.
Fantastic. Any thoughts on uni-alloy to reduce the alloy grades for steel?
I don't think it's necessary. It is very easy to recycle more or less any alloy of iron. Very, very easy. Unlike, say, aluminium, where refining is very difficult. Yeah.
Harry, for the brilliant talk and for answering all the questions. And please do, if you've enjoyed today's event, please do keep an eye out on future events, either from CSM or SC MMS. And yeah, I'm sure if you've got any last minute questions as well, please do feel free to put them in the chat. And I'm sure Harry will be very happy to answer them. But yeah, please join us again in saying thank you very much for the great talk.
Okay.